Is there any sound now? How about now? Alright, we're gonna get started here in like 5 more minutes and let people roll in a little bit more yet. What's that?
Are you streaming from like up in that corner?
Right here.
Oh, right.
So I just wanted to stream the whiteboard because I'm going to use that a decent amount. And actually, I can move this out of the way right now. So I'm going to use the whiteboard a fair amount, so if you can't see it very well, you can slide over and fill it up. Alright. You got
Yeah, I looked in there and I found one that seems possible that guys not only get together accurate. Yeah, or something. But it's got a restaurant or something. You're right.
Man, Twitch has a huge lag. It's like 45 seconds behind. 3 right now. I don't know what that should be at. Okay. All right. Can you guys all see the whiteboard all right from there? Good to go? All right. Gonna go ahead and get started. And I'm going to, Brett, can I put you in charge of this? So, we need you to swap from desktop to scene whenever you use the whiteboard.
Great. What do I hit for that?
Alt tab to get to that, and then just click on it. All right. All right. Hey everybody, I'm Garrett. So this is going to be Game and Graphics Programming 101. So I'm going to go from the very bottom and try to build up on it. So it's stuff that you guys might have seen, but I'm going to slowly build on more and more so that then everybody gets a good idea as it goes all the way up through. So I'm going to swap it to the webcam. And then, so we're going to start right at the beginning with, oh. Maybe I should just do it. Let's just distract me. I guess first of all, let's go here. Okay, so vectors. So these are the things we're going to talk about with 2D, 3D, point versus what a vector actually is, length, the normal, the dot product, which is kind of like your angle, and then we're going to figure out how you find that. Okay, let's go to the whiteboard. Okay, so a point in 2D is X and Y. So most of you have done game development, so you probably have an idea of what that is, and looking at a graph, you understand X goes here in this direction, Y goes in this direction. So if you had 1, 1, then you'd be up in this area right here. Good so far? Okay. So now the difference between what a point is and what a vector is that it's the same x, y, except for you denote it differently, because a vector is a direction. So instead of saying that we're at this specific position, we're saying that the direction goes from the center origin point out to 1, 1. Clear there? And then, so we got a point, and we got a vector, and these are in 2 dimensions, and then for the 3rd dimension, we just add z. Simple as that, and so in this case, it would be 1, 1, 0 on the z dimension. So we're not actually going down it at all. I actually have this, my handy dandy pipe cleaner thing to help display axis. So you've got yellow that's typically denoted as the y-axis, you've got blue denoted as the z-axis, and then red as the x-axis. So when you're looking, typically the z-axis will go, let's see, negative away from you. So if you're looking at a model, it's going to be negative 5 units from you. Red is the x, yellow is the y, so we'll talk about rotations in a minute. How is that? Probably can't even see that on the webcam. Bring it back just a little bit. Okay. Okay, so we got 2D, 3D, and point versus vector. So now we're going to talk about the length of a vector. We're going to make this a little bit bigger. And we're just going to keep it in 2 dimensions for now. And we're going to say that this is a 1, 1 vector. And so in order to find the length of this vector, we have to do a little bit of math. And so the math for this is, for 2 dimensions, is the square root of the first one of x times itself, so 1 times 1, plus the y of 1 times 1. So the total value of that is 2. That looks like I'm dividing them out. So the square root of 2, which I don't remember what that is. It's like 0.707, I think. If I remember right. Anybody remember what that is? 1.41. 1.41? That sounds right. 1.414. You're right. Okay, so we use that to find out what the length of this vector is. Which that makes a lot of sense to do that. So if we look at this, we can kind of understand why that's the length of it. Because if you look at here, you've got 1, you've got 1. You can pretty clearly see that the length of that line is going to be longer than 1. So 1.414 is where that kind of makes sense. Okay. So we're going to take the normal of this now. So does anybody know what a normal is? Excellent. Okay, so a normal is a unit vector, which means that it has a length of 1. So whatever the x and y in here is, when you take the square root of that, it has to equal out to 1. And we'll talk about a little bit later on why that's important, but in essence, we want to take it so then that length of 1 here, we want to shrink that array down or enlarge it. So if we had a vector array that said, okay, we're at 0.25, 0.25, then we also want to increase it out. So then we're always at a length of 1. And it comes into a benefit when you're doing a lot of these mathematical operations on the video card, because when it's down into a normal vector, it gets rid of a lot of extra math that the video card doesn't have to use, because it doesn't have to like divide out the length or any of that kind of specialness. Whereas the normal is always going to be a length of 1, so it kind of just like magically, it's kind of like multiplying 1 times 2. It's going to be 2. So let's figure out how we get to that point of normalizing it. And it's pretty easy. You just take whatever the length of the vector is, which we already found was 1.414, and then you divide each component in the array by the length. And I think that's probably where you get the point. 0.707. That's what it should end up being. Which means that when you plug these in and you multiply them together to the square root, it'll end up being 1. Is that clear enough? Should I go over that a little better?
Or you just take the inverse.
Yes, you could. So let me go over some, make it a little bit easier to grasp. Let's go back to this grid, and let's say we've got these numbers. Let's say our vector is 2, 3. So we go 2 units in the x, 3 in the y, and so we end up at this point right here. And so it's a little bit higher up than it is on a normal 45 degree. So we've got a different angle for this. So let's put our vector up here as 2, 3. And now we want to find the length of that vector. So do 2 plus 2, or 2 times 2, plus 3 times 3. And then we do the square root of that. So we got 4 plus 9, square root of that, square root of 13, ends up being, I don't even know, Google help, a length of 3.6, unless I'm doing this wrong. So the length of this should be 3.6, when this is 3 and this is 2. Which kind of makes sense. Got 3, it's a little bit longer. Good there. So now in order to turn this into a unit vector, we take that length of 3.6 and we divide each of these. So we do 2 divided by 3.6, 3 divided by 3.6, and then we get a smaller number. And then this will become the unit vector, so it'll be a length of 1 and come out to here. Okay. Yep.
So, like, what's so special about a normal besides just the fact that it's like just one unit length?
So that is what's special about it, is that it has a length of 1. It's a special vector in that it's kind of like when you take the number 1 and you multiply it by anything, you're going to get whatever that number is. It's kind of the same type of mathematical idea.
So, like, a longer vector would just be like a normal extended.
So anything that's longer, more length than that, is only going to describe direction and magnitude. So for this right here, this 3.6 is the magnitude of this vector, whereas with the normal, the magnitude is 1. So since the magnitude is only 1, it's only describing the direction, not how far the direction is supposed to go.
Okay, yeah, that makes sense.
Okay. All right, so let's go to the dot product, which makes it a little bit more complicated. The only reason I'm spending so much time on these is because they're fairly integral to the shader part when you get down a little further. The rest of the math stuff I'll go a little faster with. Okay, so the dot product, let's say we've got an array that goes 1, 0, and we've got another array that goes 1, 1. Make it easy numbers to deal with. And we want to figure out what the angle between these are. And the way that we do that is we use the dot product. And when you see it online or on websites, it's usually denoted as a really big dark circle, like a bullet point. So usually when you see like 1 times 1, it's a little dot. This one's a big dot to denote that it's trying to do the dot product. And so the dot product, you take both of these vectors, and you've got your x and your y, x and your y. We're going to call this vector u and this vector v. And usually in mathematical papers, they'll put some kind of like little arrow over them, denoting that they are vector things. But I hate reading mathematical papers. They're always confusing. So we take our vector u dot x and multiply it by our vector v dot x. And then we do the same thing for the y component by adding it. So we got u dot y times v dot y. And so we figure out what this all comes up to. And so if we do u and x, we got 1 plus a y ends up being 0 because multiplying by 0. So our end is 1. And so that right there is the dot product. And so it's some magical number when you don't know what it's describing. But so if we assume that the dot product is 1, and you go back to remembering what the sine and cosine stuff is from way back in like high school time, then we're going to use this value to figure out where it's at on these cosine and sine waves. But because of the way that we're doing it here, we actually have to do the inverse cosine. So an arc cosine or cosine inverse are both displayed the same way, or it's both the exact same thing. So we do the arc cosine of 1, inverse cosine of 1. And that will, I'm trying to remember what the graph looks like, but it's something like this, I think. Something like that. But arc cosine, the value in there I think can only be between -1 and 1. And so it'll figure out where the degree is in that. And this is pretty typical, so this is 45 degrees. But this will come out in radians, I think. Anybody know the difference between degrees and radians?
I think it's like
2?
180/5.
Yes. Okay, so you know the idea of the unit circle, where you got, when you're talking about degrees, you usually start over here and then you go counterclockwise. So a full circle ends up being 360 degrees. So for this is pi, and then 360 degrees is 2 pi, and then this would be 0 pi, and pi over 2. So when you're talking about radians, you're talking about using the pi coordinates. So if we were talking about 1 pi, then it'd come over here and it'd be 180 degrees around that unit circle. But it's also 3.14 for the radian part of that. And then to convert it, it's what is it? The radians times 180 divided by pi. Is that right? I always mix these up, and then it's the opposite of that. Pi divided by 180 times your degrees. Yeah. Yeah. So from radians to degrees, degrees to radians. Okay, any questions before I go to the next more complicated?
Okay, so in that case, we're doing 2D vectors.
Yep.
So once you have your your
Z.
coordinate,
Yep.
That's no longer going to work if you're using the that product to find your coordinate, because then you're going to be like, you're just going to get the reflection of it. You're not going to have the. Does that make sense? Like.
Yep. So if you this will still work for 3-dimensional arrays, because when you, it's hard to even.
Like it
These
will
will
be
work.
one angle, but you're going to have 2 angles. You're going to have a
Right.
theta, and then you're going to have a gamma. Like you're going to
Right.
have 2 angles.
So if you picture the 2 vectors that we had, the one going down 1 and this one going down 1, 1, if you added a z-axis to it and you just said, okay, this one's now at 1, 1, you've still actually got this plane, so there's still 2D in their respect. If you're trying to figure out the angle between 3 vectors, then that would start becoming an issue. But for the algorithms here, all you do is you just add an additional component. So the dot product here, we would just add the u dot z plus v dot z, like that. And then that would find the dot product for a 3-dimensional array. And you do the exact same thing for the length, which is that square root. So it would be that u dot x times u dot x plus v dot y, or u dot y times u dot y, and then plus that u dot z times u dot z in random space. Yep.
Correct. Like if you're multiplying 2 vectors, that is going to be correct, even if
Yep.
you're 2 dimensions. But my question is, what if you're representing some kind of object in a video game, correct?
Okay.
And the video game is on 3 dimensions,
Mhm.
right? And you have like, let's say bullets flying or some particles, something like that.
Okay.
Are you going to use, let's say, for example, polar coordinates that are going to allow you to trace a bit better and then changing it to like how are you gonna do something like that?
Okay. So that's interesting. So bullets are typically you'll have a point for a bullet where it's at in position, and then you'll specify a sphere for a bullet. But then if you're trying to figure out an intersection from time 1 to time 2, then there's a whole bunch of different things that you could do, but usually you end up creating like some kind of a cylinder type thing to say if it's colliding within this cylinder during this time frame, then it's been colliding.
Okay.
Is that
Yeah, yeah,
okay? Anybody else got anything?
So
Yeah.
if you had a 4th variable, does it go into the 4th dimension?
Probably. Actually, there is that the game name that I can never pronounce.
Oh,
It's
no, I
like-
saw that. Yeah.
Yeah,
it's like
meta.
you go through the fourth dimension. and all
Right.
that,
Which, if you guys haven't seen that, like look up fourth dimension video game, and it'll blow your mind.
It's insane.
Yeah, I don't even understand how the shaders and stuff of that work. This is gonna be so complicated. All right, so let me flip flop. Okay, so the next part we're gonna talk about are matrices. So these have a lot more numbers, but I don't think they're nearly as complicated as making, or not as fundamental to understanding as what all these are. Okay. So let's first start with, let me swap back to the webcam. Okay. Make sure. Okay. All right, so there are 3x3 matrices, 4x4 matrices, and 4x3 and 3x4 matrices. And so what these are referring to are the columns and the rows of each of these. So this is a 4x4 matrix. And so this one in particular is the special one. It's the identity matrix. And this is kind of like the number 1 in math. So if you multiply this with another matrix, you're going to get that matrix. That's all that says. So this is like your base starting point. So any kind of matrix operations that you do, you're going to want to start with this. An important distinction is for OpenGL and DirectX. They have row major versus column major. And all it really is how the memory is laid out and which direction that you go. If you go down the row first or if you go down the column first. And so OpenGL is column major, whereas DirectX is row major. So if you're following any tutorials or anything, trying to figure out the matrix stuff, that's probably your issue if it's acting wonky. Okay, so we're gonna show the multiplication stuff. So what we're gonna do, because we're gonna, instead of going by 4x4, which is a lot of numbers, you'll see why pretty quick. We're gonna just do 2x2. So we're gonna start with the identity matrix for a 2x2 matrix. And we're gonna do, let's see, 2, 1, 1, and 2. And this is a 2x2 matrix. So an important thing for the matrices here, so the 2 here denotes how many columns down it goes, and the 2 here is how many rows across it goes, or flip-flop. When you're multiplying matrices, these 2 numbers here have to be identical. So you can't multiply a 2x2 by a 3x2, but you could multiply a 3x2 by a 2x2. That makes sense, because if you had a 3x2 over here, then these 2 numbers would be the same. Okay, so for matrix multiplication, we're going to end up with a final matrix over here. And we start with going across and down. So it's kind of complicated with 2x2s, but it gets ridiculously more complicated when you're doing it by hand for 4x4s. But we're going to take this one and this one, and we're going to multiply them together. We're going to do 1 times 2. And then we're going to go over, and so we're going to go to the 0, and we're going to go to the 1. So we're going over and down. And so then 0 times the 1. And now we're done with this cell. So now we're going to go to the next one. So now we'll go down, and we'll start at 0, and we're going to multiply by 2. And then we're going to do the same thing. We're going to go over 1, and then we'll multiply by 1. And so this ends up being 2 plus 0, so 2, 0 plus 1, so 1. And then we do the same thing again. We start here, and now we go to this row, since we're in this section of it. Okay, so make sure I'm doing this right. So we've got 1 times 1 plus 0 times 2. And then we do the same thing for this last one. So we got 0 times 1 plus 1 times 2. And so we got 1 plus 0 times 2, so 0, so we got 1, and then down here 0 plus 2, so we got 2. And so our final matrix ends up coming out to 2, 1, 1, 2, which is the exact same thing that we started out with, which makes sense because we started with the identity matrix, which is kind of like multiplying everything by 1. That sort of makes sense. You don't have to understand the matrix multiplication. It's kind of like a hard-coded thing, and most of the times programmers they'll do a for loop where they'll for each column and then for each row, and then they'll do the matrix multiplication, and then the compiler usually like unwrap all that, so that's one big long like 16 array thing, which I think I want to say I've got. Oh no, I don't. Okay, never mind. Okay, so that's matrix multiplication, and there's nothing too complex about it. It's just a lot of numbers. And when it comes to graphics cards and the CPU, having to deal with, this was just the 4 numbers here, but when you come to a 4x4 matrix, you've got an additional 2 more additive operations here for each one of these cells. Plus you've got another 2 there and another 2 more on each of the sides. So you end up having to calculate this for 16 different values, right? 4 times 16, so yeah, a lot of times. So it's mathematically intensive. So the less that you do matrix multiplication, usually the better. So for a good example is when you're sending matrices over to the video card, if you can send like the world matrix, the view matrix, projection matrix, which we'll get into in a minute, you could send those all individually, and then every time they could recompile or recompute each one of those together. Or on the CPU, you could multiply them all together into a model view matrix, send that to the video card, and then it doesn't have to worry about multiplying those matrices repetitively. Okay. That's a 2x2 multiplication. So now it starts getting easier. Yep.
There are some cases in which, for scientific purposes, they use GPUs to actually compute large matrices.
Yeah.
Is it very common in video games to use the GPUs as well to do like the matrix multiplications and all that stuff and all those operations kind of to?
Yeah. So
instead of just for the graphics, but also using it for like math, renderings, and all.
yeah. So there's a bunch of different instances where you'd want to do the matrix multiplication. So anytime that you need to position an element for the video card, you're going to end up doing a matrix multiplied by a vector 4 or vector 3, wherever your positioning is, to figure out where it's supposed to be on screen. But then there's further things where you can do like the CUDA, stuff like that, which is a lot of what the research places are going to do. So they'll send a program over there and use OpenCL or CUDA, which is NVIDIA's side of it, and then come out with an answer via the video card, which is nice because video cards are run in parallel so well. Like it's like 3,000 some computers all on one little card, and they just all run the program all at once, which is why video cards are so good at doing graphics stuff, because it's all like you're dealing with so many individual pixels, but you're doing the same process to every one of those pixels. That answered it all?
I suppose the answer will be it's possible, but it's mainly used for graphics. What I'm saying is more like if you have a lot of, let's say, vector multiplication, things like that, where you have, let me give you an example. Let's suppose we do have a multiplayer video game in which you have a lot of different characters moving.
Okay.
And you want to analyze all of that as a big matrix.
Okay.
Instead of having the CPU process all the information of, oh, there's a bullet coming here and there,
Right.
is it very common to see those operations being done on the GPU instead using like linear algebra to solve problems?
So there are instances where you can like send matrices out to the video card and then do all the computation stuff, and then you take the result of that and put it into a texture, just an image. That way the CPU can read the individual color values out of that to recompute what the actual answer was. But it's not too common to do it that way, because a lot of times, especially like the bullets and stuff like that, you need to do collision detection. And so you're going to be wanting to use any kind of that math for those purposes, so it doesn't usually make sense to offload it to the video card unless you're super CPU bound. And by CPU bound, I mean like your CPU is at 100% all the time, but your graphics card is down to like 10%. If that's the case, then it makes sense to try to offload some of that, so then it kind of evens it out, and that way you can get older and older hardware support. But for OpenCL and research purposes, it would make a lot of sense to do matrix multiplication there, because but it's a whole different process, a whole different field with OpenCL, because that's more of a computation library. It's kind of like building a C library with a lot of threading capabilities. Okay. Anybody else get a quick question? Okay. All right, so we're going to talk about this 4x4 magical matrix. So we've got our identity matrix, and a 4x4 matrix is always comprised of 16 floats. You could use doubles if you really needed the precision, but most of the time it's only going to be floats, and I'm not even sure if OpenGL and DirectX support doubles. They might. But the only instance you would probably want that is if you were doing some kind of like galaxy simulation or something like that, where you need like a huge amount of number variation. So now I want to talk about what the magical properties of this are. And so this right here and this right here are your X, Y, and Z values. And so this is that difference for the row major versus column major on where they're going to show up. So for OpenGL, it's column major, so your X, Y, and Z are going to be here in your matrix if you're trying to visually look at it. And in DirectX, your X, Y, Z is going to be down here. And the only reason to know this is if you're looking at your matrices and you're trying to figure out if something wonky is going on, it makes it a lot easier to look at a matrix and say, oh yeah, my translation is down here. This is where it's supposed to be pushing it up over to. These three numbers here are your X, Y, and Z scaling. So if we did 2, 2, and 2 here, then it's going to make whatever your model is, and it's going to enlarge it, make it twice this normal size. And then it gets more complicated with rotation. So for rotation, and I could be wrong on this, I think these ones are rotation for X, this one is rotation for Z, and then I think it's like this one, this one, this one are rotation for Y. But those get really complicated and convoluted, and it's kind of hard to figure out what they are. So if you're looking at a matrix and you're trying to figure out what the values are, if it's rotation that you want to be worried about, then I would try to look before the matrix is calculated. But for at a glance, it's pretty easy to look at these for what the scale is and where it's supposed to be going. Any questions? Yeah.
Sorry, what was the bottom matrix again, or the X, Y, Z at the bottom? What is that for?
Okay, so for DirectX and OpenGL, that's the column major versus row major thing. So it's kind of like it flip-flops the matrix. So there's a thing called inversing and transposing, which I've got down there. And so when you transpose a matrix, you're flip-flopping the values on here. So if you were to transpose this one, you would take these values down here would stay the same, but then this one would come here, and this one would flip-flop to there. and then this one would do the same, back and forth. And so you'd flip-flop the matrix. So that's one way to, if you're trying to convert an OpenGL matrix to a DirectX matrix, you would transpose it. And so when you would transpose it, this X would then come up to here, this Y would come over here, and this Z over to here. Yep.
So the X, Y, and Z are vectors or positions?
They would be a position. So where you're trying, so if you took, let's say you had 0, 2, and 0. So you had 2 for your Y. If you multiplied this by a vector, like you had 0, 1, 0, and for, remember when we were multiplying 2 by 2, it had to be a 2 by 2 matrix again? Same type of thing, so this has got to be a 4 by 1 matrix in order to multiply a 4 by 4. Because these numbers have to be the same. And so we add another 1 at the end of this, which I'll talk about the extra 1 in a second. So if we took this matrix, which has got 0, 2, and 0 in it, and we multiplied it here, then it would add this 2 value, and the 0 is technically 2, and it would turn this into a 0, 3, 1. So it would be transposing or translating, not translating, moving it somewhere. Does that make sense? Yep.
And maybe since it's already, but is that last one was a 1?
Okay. So for when you're trying to translate something, to move it, the vector, so you're always going to have a vector 3 to describe a position in 3D. The 1 makes it so then you get the translation component when you multiply a matrix. If we did a 0 in here, then it would be like multiplying each one of these by that 0 instead of a 1. And so by doing that, the one good advantage out of that is that you do rotation only out of the matrix and scale, because then it's as if you were multiplying a 3 by 3, and you get rid of all these translation vectors. So for a vector 4, when multiplying, 1 equals translate, 0 equals rotate and scale. And we'll actually get into that just a touch more in a minute. Briefly mention.
Does the 1 also mean rotate and scale?
Yes, yeah, yep. So the 1 makes it so then it also gets the translation. Okay, let's talk about what the inverse is. So taking, which I don't even want to bother trying to show what the math is because it's a lot of hand jam work and it comes out to like a huge amount of things to find an inverse for a matrix. But let's say, so we know what the identity matrix is, and we've got our matrix up here. So the inverse should make it so then when you multiply this matrix with the inverse matrix, it becomes the identity. So you get the 1s all the way down again. Finding the inverse matrix isn't complicated. It's basic linear algebra type stuff where you say, okay, if this is a 2, what do I have to do to make this row? What do I have to subtract from it to make it a 1 again? And if you guys are really interested in doing that, you can Google it, but it's kind of a pain and it hurts your brain because you can mess up fairly easy. Okay, projection and view matrices. So a projection, a view matrix, and a world matrix are all comprised of these 4x4 matrices. And so let me erase all this. Okay. So there are a whole bunch of different spaces. So you've got object space, which is if you've got a model and you want to move like the cap on this, for example, we'd be in object space if we're dealing, like say we were in Blender or something like that, we would be dealing with the object space of where this is in relation to the object itself. After that, you get to world space. And world space is the position of, if I've got a game and this is my center point, I want to move it 2 units to the side. That's world space, moving the whole object itself around in the world. We go from there to view space, which is what your camera is and where that's looking. So if we've got our bottle and we moved it over 2 units, then that's in the world space. To convert it into view space, we got to take our camera vector, camera 4x4 matrix, and we say, okay, my camera is now here, and so now we use that to multiply the world's position and figure out what it is in the camera's view matrix position. Good so far? And then there is screen space. So screen space is you've taken your object, you've positioned it into the world, you've told it where the camera is looking in relation to the object, and now we need to position it, we need to show it on our actual window. So when it comes all the way down through, you end up with this screen space that positions this little object in the center of the screen, or wherever it is in relation to the camera in the world space. Okay, so each one of these, other than the object space is just relative to the object alone, each one of these, to convert this object's position, you multiply it by each one of these 4x4 matrices. In which the screen space, to get to there, you multiply it by a projection matrix. And the projection matrix is it takes like the width and the height of your window, figures out what the aspect ratio is by W divided by H to figure out how much it should scale. You got 21 by 9 or 16 by 10 resolution. And so when you multiply the projection matrix and you rasterize everything out, which we'll get to, it figures out exactly where that specific pixel should be drawn on your window. And these get important with the inverse matrices we were talking about, because if you get all the way down through your shaders and you get to the fragment shader, which we'll talk about, you've got a specific pixel that you're looking at, but you need to figure out where it's actually at in relation to the world space. Then you would take your position that you know about there and multiply it by the inverse of the projection matrix. When we saw that, the inverse of the matrix, when you multiplied it by its inverse, it created the identity. So if we multiplied the projection matrix, the full position that we got, by the inverse projection, it'll be as if the projection never actually happened, which will bring us back to the view space. And then we did the same thing with view space, did the inverse of that matrix, and bring us back to world space. Good so far? Okay, what else I got? I think that's all I've got for the matrices. Yep.
So some engines, they have nested objects. Does that just mean you have to do the object matrix multiplication that many times?
Are you talking about a mesh or a model or like many objects in a world?
Like a game object, and you like nest objects under it. And so when your main object moves, the other ones under it also move and rotate.
Right. So that for that should be like object space for the model itself. But you could also have multiple world space objects, which is, so what you're talking about is more like a hierarchy, where you've got like a parent.
Right.
And so any objects within here are going to get multiplied by this 4x4
so
world
you
space
have to have
matrix,
separate
which would then
4x4
be
matrices
multiplied
for
by each
each
child.
parent object.
Yeah, exactly. Yep. Yeah, which that's kind of the same lines of what skinning animation is.
Imagine that can get out of hand.
It can. Yeah. Any more questions? All right. Let's go next here. Okay, quaternions. So we're going to talk about Euler angles, which is not Euler, even though I still say Euler all the time. And it's only called Euler instead of Euler because there was some like German guy that came up with it or something along those lines. German or Russian, the smart people. Okay, so we've got our axis. So we've got y, x, and z, which is the same thing here. We've got red, x, blue, z, y, yellow. And when we talk about rotating for Euler angles, we're talking about rotating around this axis. And so if we take the example of the bottle and we rotate around the yellow, the y-axis, we're rotating it around like that. Actually, I should the bottle before I keep rotating this. Okay. So we rotate it around that y-axis, and then if we wanted to rotate around the z-axis, we would rotate like that. If we wanted to rotate around the x-axis, then it would go around like that. So you're rotating around the line rather than with it. And now I'm going to show. Does everybody understand Euler angles well enough? The idea that you can kind of position something in space with those three numbers. Okay, so I'm gonna try and show. Oops.
Nice background.
Thanks. Okay, so I'm gonna show why Euler angles are bad. So I couldn't find a good example of this to show, so I had to build something. So this is with my own engine I've been building. And so we've got the x-axis like we were talking about, the y-axis, and the z-axis. And one important note is up here, you can see it's y, x, and z. So you can multiply these in any order you want, but you'll see the y-axis is the one that's the bigger one around, and then you've got the x, and then you've got the z. And depending on your game, you could multiply them in different orders. It doesn't really matter. They're going to end up in whatever space you want, but they are dependent. Like if I rotated the x first and then rotated the y and multiplied it, like flip-flop these, then it could change where the actual rotation ends up. So this is all fine and dandy because you can, and this is what most engines or anything like that's going to show are these Euler angles so that you can position it, like Maya or Blender or 3ds Max, any of those kind of things. These are the numbers that it's going to show you because it's got quite a bit of degree of freedom. You can position it wherever you want. The problem comes in with the gimbal lock. So gimbal lock is when you've got two axes. So we've got the x-axis or the z-axis, sorry, and the y-axis are at the same point. So right now, if I wanted to rotate this guy so then he was standing back up and facing that direction, then we would want this gray axis to be available. We want to be able to rotate him up like that. But because we've only got the y, x, and z, and the y and z there are already locked, we've lost a degree of freedom to position him and rotate him back. But since we've still got Euler angles, we can still get him to that point. But watch what happens when we go to them in a linear fashion. Now you see how as he was laying down, he kind of like wibble wobbled back up. And I'll show that again going back. So that's what gimbal lock does. You can still get to all the positions, but you're going to get some wonky movement, especially when you're talking about camera rotations and you start looking at different things. And especially when you start like looking straight up, you'll all of a sudden start snapping or you'll be rotating a little goofy. And so that's where quaternions come in and why they're nice, because it solves this gimbal lock. Anybody have any questions on this? Does it make sense what the gimbal lock is? Yep.
So for the most part, quaternions are going to be used to determine rotation in a more effective way than the physics rotation.
Correct. Yep. Yep. Okay, so let's go back to Euler angles. or the quaternions. Okay, so we got gimbal lock. So now quaternions get confusing because with Euler angles, you just had x, y, and z. And so when you look at quaternions and you see, okay, now it's got 4 floats, and all of a sudden you've got this magical extra number in there, it doesn't make a whole lot of sense as to what it is or how it works. And that's where a lot of the confusion gets in. So before you get further, you have to imagine, so this is w, x, y, and z. Or it can be x, y, z, and w. It shouldn't actually matter if you're dealing with quaternions unless you're building the quaternion library or you're trying to follow some tutorial website, because these can flip-flop depending on the engine. So for like mine, my engine uses XYZ W versus the WXYZ, which it makes sense to do W first because alphabetically, but it always made sense to me to specify, okay, here's my XYZ and here's the W sort of kind of tells you how much to rotate. So we'll talk about that in just a sec. Okay. So we'll go back to our handy dandy pipe cleaner axis. So with Euler angles, you have this fixed axis where y is always pointing up, x always to the right, z always going down. Makes sense. But for quaternions, you actually specify the axis that you're rotating on. So if I wanted to I could say, okay, now my y is actually going to be pointed like this. And so now if I've got my bottle here and I wanted to rotate on the y, it would actually do some kind of like a rotation like that, trying to rotate around this yellow. That makes sense? So the reason the quaternions are so powerful is because they're not fixed on that specific axis. And so when you start rotating and specifying where it's actually supposed to be rotating around, you can get some unique rotations. But then furthermore, the quaternions can be multiplied together. So you could specify that rotation, say, okay, now I want to rotate on the x. Now I've got a different axis. I want to rotate on the y here. And so then it opens up a lot more freedom because then you no longer have that gimbal lock because you're not restricted to a certain axis. Make sense so far? Okay. Now, let's see if I can, actually I think I wrote it down even. Yeah, okay. Okay, so we've got our x, y, z, and w, wherever you want to put it. Okay, so w equals cosine of whatever your angle is divided by 2. And then your x equals the sine of your angle divided by 2 and then multiplied by this x that you specified. So in which x would be whatever this axis is. And then your y and z are the same thing, just replacing the y and z here. So this is why the w kind of sort of is what your rotation is, because it plays a role on w, but it only plays part of the role in the x, y, z. And now the other important thing to note is that, like on the screen here, you see it starts with a 1 for the w. That's the same thing as the identity matrix again. So you multiply that with an arc quaternion, you're going to get whatever quaternion that was. But then on top of that, whenever you specify the axis and the rotation for quaternion, the quaternion is going to end up being a unit vector. So the entire length of this, which if you do math stuff, it double lines around something, means you want the length of it. So this vector, it's always going to equal 1. So, which is an important property and kind of makes sense because if you think about the cosine and sine waves, you're never going to get more than 1 on either one of them, and you're multiplying everything around the idea of going in a circle. Okay, so an interesting thing about quaternions. So in Euler angles, you've got your 360 degrees. In quaternions, you actually have 720 degrees as a full circle, which I didn't know about until I saw a cool video. Do the awkward belt trick. Okay. So, I thought it was weird, but there's physical reasoning behind it in nature of doing, so if I twist the belt a full 360 degrees, then it's all twisted up. But if I twist it another full amount, and then I take it without rotating the top again, and I flip itself back on its head, it goes straight again. So that's the whole idea of 720 degrees, of by only translating it, I get it back to the zero amount. But if I were to do 360 degrees, and I do the same thing with only translating it, it actually goes in reverse the 360 degrees. So if I rotate again, I'm back to zero. Make sense? Fun facts. Okay. Quaternions. Anybody got any questions before I move from quaternions? Okay. All right. So now we get a little bit out of the math stuff. Okay, so we're going to talk about vertex and index buffers. Okay, so on the video card, whenever you've got data on it, it's called just a buffer. There's data on it. It could be all zeros, it could be all ones. It doesn't matter to the video card. It's just a buffer of data. And then based on the drivers or your program, it's going to specify what that data is. And so we've got vertex buffers, which is always going to contain data that specifies the vertices. So if you've got a triangle, each one of these points are the vertices, or a vertex. Vertices multiple. So these are going to specify like the positioning, for example, which you could do two-dimensional triangle in OpenGL, DirectX if you want it. And so we need to figure out a way to store this data on the video card so then the video card can use it, and that's what the vertex buffer does. And so we need a vertex declaration. And so for the example of this one, we're using, let's have it. We're using a vector 2. So we have an x and a y. And let's say that we also want to color this triangle. So we've got R, G, and B to color it. So we could do, like, this corner is going to be red, this one will be green, and this one will be blue. So in order to show that, we need 3 floats, and so we'll just use a vector 3. So we've got x, y, and z, or R, G, and B for that example. And so for these, for the x, y, and z, these are all float values. And so floats, depending on how much you guys do for programming stuff like this at a low level, if you do a size of in C and C++ of a float, it'll equal 4. And the reasoning for that is because you're dealing with bytes. So it's 4 bytes. So 4 times 8 equals 32 bytes of data in a single float. And so each one of these has x, y, and z. I think I'm getting this right. So we've got 5 floats that we want to define per vertex here. And so this comes in handy when you're trying to describe this vertex declaration. Because now we're specifying a single, kind of like a block, saying, okay, here's my vector 2, this is a position. And here's my vector 3, this is a color. And now we're going to describe this as the vertex declaration. And the only reason to need to understand the size of float thing here is because when you're dealing with vertex buffers, like I said, it's just data to the video card. They don't need to understand that it's positioning or color or anything, but you will when it gets to the graphics card and the actual shader programs. And so for this, we would need to specify where these offsets are. And so for vector 2, with a position, we've got 2 floats in it. And so we've got that value of 32. So we multiply this, because everything is in bytes for the video card. So you multiply it by 2, and so you come up with 8, because there are 8 bytes in this vector 2. And so this would start at 0, and this would start at position 8 within each vertex. And so then the entire stride is another 3 floats added onto that, so another 12. So this would be a position of 20, meaning that every single vertex in our vertex buffer is going to be a size of 20. And so that's how the video card knows to step from vertex to vertex if there's multiple of these. So you got another position and color. And then for this specific triangle here, we would have another position and color. And so we would have vertex 1, vertex 2, and vertex 3 all within this one vertex buffer. Make sense so far? Any questions on that? Okay. All right, so we're going to go to describing the triangles and how they're made up. Okay, so on the video card, there's 3 different, or at least 4 different ways rather. You can specify points, which is kind of like if you were doing a particle system or something like that. It could be handy to use this in conjunction with geometry shaders and stuff to display information on the screen. You could do lines, which are handy for like showing wireframes of your meshes and stuff. And then you've got triangles, which is what everything in a game is made up of, whether it's a quad in your Blender or Maya or whatever, it's going to end up being converted down into a triangle. There are also fans, which specify a starting vertex, and then you specify a second one, a third one, and then the fourth one says, okay, use the first one, the last one that was entered, and then this current one, to then build out multiple triangles all based off of this one. So this is a fan triangle, a line, and a point. And then there's one final one, which is a strip, meaning that you just take the current and the last one to create another triangle. So we've got that one and that one. We could then specify another triangle off of that, and then specify more triangles. So rather than, well, actually that didn't, I ended up creating a fan. Let's do something like that. So that would be a triangle strip where it's sharing the previous 2 vertices of each one of the triangles. That way you only have to specify one more additional vertex to create another triangle off of that. So you got triangle 1 off of these 3, and then triangle 2 off of these 3, but you only had to specify this additional 1 point to create this additional triangle off of it. Okay. So now we're going to talk about the index buffer that pretty much always goes along with a vertex buffer. So if we've got this quad, and we've got these 4 vertices, if we were to stick with this triangle, we would have this triangle created of these 3 vertices. So we'd have 3 vertices there. But then to create the second one using this method, we would have to specify these vertices again, which would add another 3 vertices. So you'd have a total of 6 verts total in order to make up this triangle. And so where index buffers come in is it says, okay, let's say that this is 0, 1, 2, and 3, then we can make up a triangle. If we say we do an index lookup into 0, 1, 2, we'll generate this triangle. And then if we were to do 1, 3, 2, then we would create this triangle. And so this is one big long buffer. It has two triangles, so when you tell the video card, I want to use this index buffer, you say draw 2 elements. So 2 triangles using these. And then it'll use the vertices up here. But since now we've got this index buffer, we don't need all 6 vertices because these 2 are the same vertices, meaning that we can cut this 6 down to 4 vertices. And the big reason for this is if we remember back to the size of this, it was each vertex was 20 bytes of data. So that position, that color. So right there alone we've got 80 bytes there. Before we had 6, so we had 120 bytes before using the index buffer. And here you can use shorts or integers. So each one using either 2 or 4. Since this one is so small, we can choose to use shorts, which is only a size of 2 versus the size of 4, meaning that we've got 6 values times 2, so that's 12 bytes. And so you add those together, so you've got 96 bytes of data that has to get sent to the video card versus the 120 bytes that was sent with just the vertex buffer. And you can see with just this super simple quad, we've already saved 24 bytes of data, which if you imagine models nowadays, every in-game character is going to consume like 3,000-4,000 triangles. And so this 24 bytes can become megabytes of data that no longer has to be sent to the video card. And so that's why the index buffer is super important. And even with the 4 bytes, if we were to do 424 instead of the 12, you add another 12 to that, and you've got 108 bytes. So you've still saved 12 bytes even if you used full 4-byte integers. Any questions? Okay. All right. Now into the more fun part, graphics and shaders. Actually, flip-flop. Go back here. Okay. So let's go down the pipeline for the video card. So we've got these vertex buffers and these index buffers, and we send that video or that data off to the video card, and we get back handles like, okay, this is going to be handle 0 and handle 1, and that the graphics card will figure out, okay, it's in this position in memory and this position in memory, and it'll figure out when to use them. You tell the video card that you're binding to them, meaning it's like the active vertex and index buffers. So when you make a draw call, and you say, okay, I'm using this vertex buffer and this index buffer, now draw 2 primitives, 2 triangles, whatever those elements are. And so it'll pass in 0, 1, and 2, and it'll pass in each one of these verts that it indexes off to. So each individual vertex is going to go through the vertex shader. So it'll hit vertex 0, it'll run the vertex shader off of it. Once it's done with that, then it'll go to vertex 1, and then vertex 2, and vertex 3. Although it does it much more rapidly than that because it does it all in parallel. And so this is a super simple implementation of a vector, or a vertex and fragment shader in OpenGL, which does what we were talking about with doing position and color on a triangle. So we've got our in for a vector 3, a position instead of the vector 2 that we were talking about, and in for a vector a color. So this will be on the first position of the vertex, so that position, and then a color will be in the second slot. So it'll figure out how to connect the dots on those, which you can specify in these shaders for both DirectX and OpenGL what the layout of the vertex is supposed to be, or you can do it in the program side, CPU bound, to say this is the vertex layout in the shader. When we get down to here, we got a uniform of matrix 4. So a uniform is just a value that you can set on the shader that will be used for all of the vertices and index buffers but it can be customized per draw call. So say you wanted to draw a red triangle, you could set a uniform color of red, and then you could do another call saying, okay, I want it to be blue now, and now draw the triangle. And so we'll call it a red and blue triangle. And then we specify an out, and then we do this. So for this, we've got a matrix MVP. And so these are the model view and matrix, or model view projection matrices that we were talking about before. It's just all multiplied together. So you do world times view times projection, creates an MVP matrix that you can then pass to the shader, so it doesn't have to do that matrix multiplication every time for every single vertex. And then you multiply the position that we got from the triangle. So whatever this position is, it takes it, multiplies it by our MVP, so then it converts it from that object space to world space to view space to screen space, so then we know where it's going to be at on the screen. And then we just pass along the color here out to the fragment shader. And then so the fragment shader is your pixel shader. So if we look here, we've got vertex shader, tessellation shader, which is a newer, actually tessellation and geometry shader are newer things. So tessellation shader will increase the fidelity of an object. So if you were to pass like a sphere, for example, you only had say it was a super low quality sphere, so it looked like a cube. You could use the tessellation shader to add more data. Maybe I'm flip-flopping this. I can't remember if it's tessellation shader or the geometry shader. I don't have a whole lot of experience with both of them, but they'll add detail and depth to the objects.
Yeah, it's tessellation.
Yeah, you're right. Okay, so yeah, tessellation would be that, and the geometry shader is the other way, where it'll actually add primitives to it. So, like if, for example, the particle system, if you had if you specified only the 3D positions, then you could use the geometry shader to then say, okay, I want to build a quad out of this, and then that will get passed through. That way you send a lot less data to the video card to create this particle system. And so once it's gotten through the vertex shader all the way down through, it does primitive assembly and rasterization. And so the primitive assembly is basically this stuff, creating the triangles, figuring out where it's at. And then the rasterization part of it is, so you guys seen software rasterizers before? Something like that. So it's the idea of kind of like scan lines almost. I'm pretty sure that's the way that graphics cards still do it, is they'll go line by line across the pixels, figure out, okay, this pixel is marked, this one's marked, this one, this one, and it'll figure out all these different pixels that will get passed down into the fragment shader. And once it gets to the fragment shader, it does some interpolation magic. So it'll say, okay, here's my position up here was 0.5 and 0.5, and down here is 1.0 and 0. And so if I'm looking at this specific pixel here, if I passed the position here in, when it gets down to this point, position will be halfway in between, so it could be like 0.75 and 0.25. Which can be important for when you're dealing with normals, which we'll get to in a minute. So in this program, all I'm doing is taking the vector, or the V color, which is varying, just a value that can go back and forth, kind of like a uniform. And that gets down to the fragment color, and I just output whatever the color was. So if I set the color here to be 100, so 1 for R, 0 for green, and 0 for B, for blue, then it'll output just red. And so that's all that this would be, is just a red triangle. No shading, no lighting, no nothing, just red pixels. And then after the fragment shader, you get to the sample operations. So that's where anti-aliasing and comes in, which is, if you like, especially like MS Paint or something like that, if you can imagine using the pencil tool, where you can super see the stair stepping thing, that's when it's aliased. And anti-aliasing is kind of smoothing that whole thing out so it looks smoother. And by doing that, it takes the pixels to the side of it by sampling them. So it'll say, okay, what was the value in this pixel, what's the value in this pixel, and this pixel, and this pixel, and then it'll say, okay, let's make this a light gray instead of black. And that's how it does any aliasing, in essence, which, if you've seen, there's like MSAA X16 or something like that, the giant numbers that would then kill your video card. All that that's saying is that when you've got this giant grid of pixels, it's going to take a look at like this pixel right here, and if it's 16, then it's going to look at the 4 pixels surrounding it in either direction. So there'd be 16 different fragment points that it's going to touch and figure out like all of these, and then it'll average them all out to then create an aliased version, or an anti-aliased version. Okay, so when you take this vertex shader and this fragment shader and you compile them, which I'm pretty sure that happens for DirectX too, but for all OpenGL stuff, you take your code for your shaders and you compile them into a program. So the drivers and the video card will determine how the program gets compiled down, because it can vary from video card to video card, and then like NVIDIA and AMD, they can manipulate your program while it's compiling to optimize it, so then it'll run better, which they do that constantly for newer games. Like Skyrim, they were all over that and optimized it like crazy. But when you do that, it becomes a shader program, which is basically an effect, whatever runs on your video card.
For the anti-aliasing, like, if you have like MSAA like ×2, is that basically it renders it twice, kind of?
It doesn't render it twice. It just does 2 lookups. So it'll look up twice in either direction then, and then it will take the average of those, taking these ones into more consideration, but then using these ones like slightly less, and then taking an averaged point sample of them to figure out what the approximate value for that should be.
Yeah,
So it's almost like a blurring thing, but it has a little bit more edge detection stuff.
That's amazing.
Yeah, so and I'll actually talk about this in a little bit too, is when you do MSAA, it actually takes the primitive data. It's not even looking at just the pixels, it's looking at the primitive itself and figuring out that this is the edge. And so it should be doing the MSAA on these parts of it. And then it'll completely ignore the middle of the triangle, because that shouldn't be any alias. That there's no edge there to try to alias or un-alias. Good?
Yeah, that makes sense.
All right. All right, so lighting. To kind of start breezing through stuff a little bit more here. So this is your ambient, or just color. This is the diffuse, which is what your lighting is. I think I forgot to change it last time too. Oops. Okay, so for diffuse lighting, you have to imagine, let's say we've got this triangle. Now imagine this triangle laying flat, so we're just going to draw a straight line for it. So this is the triangle laying flat on the ground here. Now we talked about what a normal was, and how to normalize a vector. So when you're talking about a triangle and on the video card, a normal is going to be the direction that a face is pointing. So most of the time, you're going to be going perpendicular to whatever your primitive is. So if you had the vector or normal here, it would be pointing straight out from the triangle because it's completely flat. And so perpendicular out from it rather than parallel with it. And so these normals are when normal maps come into play. So those textures that you always see that are bluish and yellow, green, whatever stuff, those will change these normal vectors. So it would, per sample, like if, remember when we were rasterizing out, say that we were in this specific pixel here, it would, our normal map might say, okay, let's push our normal off to the side just a little bit. And we'll see why it's important here. Because with diffuse lighting that we've got here, it's finding out wherever our light source is, and it's going to find the vector between our fragment position and our light's position. And then we find out what the angle is here. And so you guys remember when we did the dot product? That's where this starts coming into play. So if we did the dot product between the light direction and our normal, we would get a value between -1 and 1 or something like that. And then if you did you typically do a max value of 0. That way, if the dot product does go below -1, it doesn't screw anything up. So you're always going to have at least a 0, if not up to a 1. And what that'll do is, as the angle gets down further, so if my light source was out here instead, my angle is going to be a lot bigger. So I'm going to have, and the way the dot product works is it goes kind of backwards from what you think of an angle. So the bigger this is, the bigger the dot product itself is going to be, or smaller rather. The closer it is, the bigger the dot product, meaning that the closer the light is to the angle. So when we take that and we multiply it by the intensity and the color and light on and all that, as we move the light around, it's going to light this specific pixel up more and less, just based off of this normal vector and this light direction. Does that make sense? Good so far? Okay. So that's basic diffuse. And then you've got specular lighting, better known as Phong lighting, Phong reflection. They're basically the same thing. Let me see, I can actually go down what that was. So Phong light is the essence of the same type of thing, but also using where your eye is at. So you would send the eye position to it and figure out where you're at in regard to the light direction and the normal to figure out just how sparkly, shiny the light bouncing off of that should be. And there's also, so it's, do you guys care about the numbers or the math behind that at all? Do you guys want to see that?
Yes.
Yes? Okay. All right, so we'll walk through that quick. See if I do have it. Okay. All right, let's go through it quick. So we've got, when we're in our vertex shader, we're going to pass through the camera position. So this is our cam position. So we pass that to the vertex shader, and then every time the vertex gets passed through, it's going to send that camera position down to the fragment shader. And the fragment shader is then going to say, okay, I'm at this specific pixel. Remember, we've got that interpolation stuff to worry about sometimes, which will deal with the normal here. Well, we've got this camera position, and we've got the position of this point right here. So we're going to take the cam position, and we're going to subtract our position, the fragment's position, to come up with a view direction. And all that means is it's where we're at in relation to the camera and the pixel that we're currently operating on. So once we get from there, we get a reflection and reflect direction. Okay, so this was some crazy day. Oh, I did. Yeah, I even wrote it down. A lot of the times, this is stuff that you end up copy pasting, so you don't have to use it very often. But it's the the light source minus 2 times the dot product of n, your normal, and the light, and then times your normal again. And so that will create a reflect direction, which in OpenGL, the reason you never have to use this is because they have a convenient method that's just reflect, and you use your n, I, and n. So I is your light source. So wherever your light positioning is, down to your normal will create a reflection vector. And so you use this reflection direction to figure out what the specular is. And this is some like crazy. Okay, so the power of the max of the dot product of the view direction and the reflection direction with a max value of 0, and then you can do up to the power of, and typically it's 32, but you can play with that 32 value, and what that'll do is it'll make these little specular spots bigger and smaller. So the power is like kind of like ramping it up. And so then once you're all said and done here, we've got our ambient value, our diffused light value, and then our specular value. So our final color that gets sent out of the fragment shader becomes this ambient light, which is just this color, or the ambient could also be a texture lookup, so any kind of texture map that you'd have, you could also look up that specific point for the ambient, plus the diffuse, plus your specular amount, and then you multiply that by the end color that you wanted it to be. So if we wanted this to be red, we could multiply that out. Yep.
So is this process any different from ray tracing?
So this is all approximation stuff, which is a significant thing to note. With ray tracing, it's so for rasterization, we're actually going backwards from ray tracing. Ray tracing is going from the position on a window, so a specific, we say, okay, I want to start with this specific pixel, and then I want to use this camera, and then you figure out, okay, my ray gets cast down out, and actually it'd be more like in that direction or something. And then you figure out from there, okay, did I hit a triangle? If I did hit a triangle, at what point did I hit the triangle on? And then you calculate this stuff off of that. And then you would do the same thing for every single position on here. But then it gets more complicated because with ray tracing, you always want to do, like, ray tracing is all about getting realistic graphics. And so you've always got the idea of, and even here, you've got like this dark crevice where the shadow is getting blocked in between the paper and the whiteboard, which is global illumination. And so as it hits this triangle, it could be a mirror, or it could be just metal or something, but it could then bounce and hit yet another triangle, and then from there it could hit another triangle, and maybe it stops at that point and you're lucky, but you could decide how many bounces, bounce 1, bounce 2, bounce 3, that it takes to then figure out what this final color is for that individual pixel. Which, when you're talking about, like, say 300 by 200 pixel window, which is itty bitty nowadays, that wouldn't be that bad. You could do that for most games depending on how well or how dense your scene was and stuff like that, and how well you're with the scene graphs. But when you're talking about 1080p and 4K displays, doing that for every single pixel is way too time consuming yet. So by flip-flopping it and saying, okay, here's my triangle, now let's render this triangle out to the screen, we'll just do an approximation of what the values are. It dramatically speeds it up. It's not going to be anywhere close to as accurate as ray tracing, but it'll be roughly close. Any more questions? Okay. All right. So this was Phong rendering. There's also blend Phong rendering, and so blend Phong changes this up a little bit. So let's say our camera, where we were looking at it, was over here. So you see the angle here is quite a bit more, a lot more than 90 degrees. And so the camera, or the dot product, likes to work within a 0 to 90 degree radius. Otherwise you start going backwards in that whole like cosine sine wave. You start going negative back and forth. So there's a way that you can take the eye position and the normal position and do a half vector. And by doing a half vector, which is halfway in between those, you can then do the dot product off of those, which creates a gentler fall off range for the lighting. So, which is the only difference between a Phong shader and a blend Phong shader. And all that's doing is just trying to get away from the issues of the dot product for approximation. Okay, so I wanted to talk about vertex lighting versus pixel lighting. And so it used to be, so the Phong shading here is only Phong shading when it's done in the fragment shader. When it's done in the vertex shader, then it becomes garage shading. I think I'm saying that right. Which you can see here, which I should probably change that. Okay, so now you can see here, it almost looks like a diamond shape here with the light. So whereas here, it's all completely smooth and nice. It's because this vertex here is completely lit, but then this vertex here is not as lit. And because of the way that the vertex shader passes down to the fragment shader, it interpolates everything. And so it thinks that this one's fully lit and this one's not, so it's going to try to ease out of that. And then all of a sudden, this one's not lit at all. And so that's why you get these sharp lines in here saying that these are lit and these ones aren't. Whereas with the fragment shader, you're going all the way down to the individual pixels, so you're going all the way down through these. And so you won't get these sharp lines. And the reason, so it's not done as much anymore because video cards are so much more powerful now, but back then, back in like the early 90s and such, doing per vertex lighting was almost a must because then you only had to do it on a per vertex base rather than per fragment, because in most cases you're going to have far less vertices than you are fragments. Good so far? Oh, over there.
So some games these days use kind of like a low poly feel, but they go back to a per vertex.
Usually not. They could, but even then you're still going to get the same thing because you've still got the idea of using a quad, even with low poly. Unless you did the funky like triangular low poly thing.
Quads instead of tries.
Right. And so in the same instance, yeah, if you're doing the low triangle thing, then yeah, you totally get away with it.
So that when you say fragment, that's referring to each pixel on the screen?
Correct.
Versus the, okay.
That's a good thing to talk about, actually. Okay, so in a video card, you don't actually refer to pixels when you're rendering. You're talking about fragments, which are technically different. Because I need to erase stuff. Okay. So if we were to look at a very, very tiny screen, each one of these are pixels. But when we talk about a fragment shader, we're actually talking about the spots in between here. And so you'll actually see in a couple of different shaders that you might look at, they'll figure out what, so I guess actually technically, so there's pixel and pixel shader, which really is just a fragment shader. but then there's a pixel, and then there's a texel. I guess that's more what I'm referring to is the texel, is what these individual things are here. And that's what you're going to end up dealing with on the fragment shader, are these texels rather than the end pixels that get printed out. And the reason that this can be important is if you're trying to get pixel precision, then you actually have to figure out what the density of your individual pixels are, which is like 1 divided by your width and 1 divided by your height, to figure out how far in each pixel is, and you just divide those by 2. And so then anytime you've got the positioning within here, you would just subtract each of these from it to move it back up into the pixel perfect location. But by doing pixels like that instead of the texels, it's something to do with the anti-aliasing stuff where it makes that smoother in the rasterization process, but I don't remember that very well. Does that help?
Yeah.
Okay.
Yeah.
Question.
Yep.
So, in the pixel shader, if it's using normals, then why does it show up any different than the vertex one if they're just using flat normals?
Because if the lighting gets calculated here, so okay, so let's say I have these vertices again, and I've got my light source shining down, and I get to here, and my light source is going to have a cone that hits like this. When I get to this vertex, we're going to say, okay, yeah, I got lit, I'm perfectly lit, so we're going to do a 1 for brightness, shining. But we get up to this vertex, and it's not getting hit at all, so it's going to do a 0. So since the lighting amount is calculated in the vertex, it passes it along to the fragment shader, saying, hey, my lighting is 1, and it says, hey, my lighting is 0, and so it interpolates these values down, saying, okay, 1 to 0, okay, so even at this point, I'm partially lit, 0.2 or something like that because of this, and then even at this, I'm lit 0.1, even though it's outside of the lighting because of that interpolation.
Okay, yeah, that makes more sense now. I get it.
And so then, but if you did fragment shading, then based on this cone, this would be like directly on, so this would be a full 1, but then it would slowly do a drop off to the point that this was 0, and then this would always be 0 all the way on through. And so it's more of like a gradient thing rather than this full like, okay, I'm lit and now I'm not lit, meaning that these both had thought that they were fully lit, these both thought that they weren't lit at all, and so it gets that sharp change there when these ones were fully lit. Okay. Oh, it's already there. Oops. Okay, so post-processing. So this gets a fair amount of attention because it's the most visually appealing thing that you can do pretty quick with like bloom processing and blurring and motion blur and all that kind of stuff. And this is like super, super simple. When you render out your triangles, you're always rendering to a specific target. So this is what we're going to call a frame buffer. I think there's a different word for DirectX. I don't remember what it is. But in essence, a frame buffer is just a texture or an image. Just a frame buffer is specifically meant for the video card. And so whenever you're rendering, it goes to a frame buffer, regardless if you've created one or not, because that's what goes to your back buffer, which is where your whole swap chain comes in. So have you guys heard of double buffering and triple buffering for your video card? You've probably seen it in game settings at some point. And in essence, what it does is that it says, okay, I've got frame number 1 here, I got frame number 2, and if you've got triple buffering, then you've got frame number 3. And this was more important back when there were like CRTs and stuff, where scan lines and stuff like that were a bigger deal. With LCDs, it doesn't matter nearly as much. But it would come through and it would render frame 1, render frame 2, and render frame 3. And then at this point, it would say, okay, display frame 1. At this point, completely flip it and display what frame 2 was. And then at this point, display what frame 3 is. And this whole time, when it displayed what frame 1 was, it was rendering whatever we wanted to frame 3. When we got to this point where it was displaying frame 2, it said, okay, render all of our stuff to frame 1. When we got to this point, it said, okay, display frame 3 and render everything to frame 2. And so it's the idea of flip-flopping the images, so then before, when it was CRTs and there's lower frame rates and everything, you would get like the horizontal break lines and things would get jittery. By doing the frame buffers like this, letting the video card just flip where it was looking at for data, it would make it a lot more like a buttery feel at the time. Now with LCDs and stuff, everything's so much faster that doesn't really matter that much. But the same idea is applied for frame buffers, where a frame buffer is just what you're rendering to. And so this is typically your back buffer, which is what the video card is going to display. So anytime you see like there's a present or something like that, present or swap buffer, that's what it's talking about, is it's going to display this back buffer on the monitor. It's going to tell the video card to push that out. And so usually with a swap buffer, or present, you'll have 2 buffers. So you'll be rendering to one, displaying the other, rendering the other, flip-flopping back and forth. Usually you don't see the triple buffering anymore. So when it comes to post-processing, instead of using our default back buffer as the frame buffer, we create a new frame buffer. We render our triangle out to this, and it could be any size you want. It doesn't actually have to be the same size as the window, unlike the back buffer. Back buffer should usually always be that, unless you're doing something crazy like that dragon game, whatever that was. The one that killed it, like Unreal. What was that game? I can't remember the game, but it kills like every PC that tries to play it. But you could technically render like a 320 by 200 scale frame buffer, and then just enlarge it out. It looked like super pixelated and garbage, but you could do it. So you'd create this new frame buffer, render the triangle to it. You would then send this frame buffer out to our vertex shader. Our vertex shader would then pass it down. So we would create a quad that is the size of the screen, which is also the size of the fragment or the frame buffer that we created. So our triangle would be rendered on this quad. So when we've got that texture created, we pass it to the vertex buffer with these 2 triangles and this texture that's overlaid on top of it. We can then go down to the fragment shader and start modifying the individual pixels. So if you look here, that's what they did. They created a frame buffer here, a frame buffer here, frame buffer here, frame buffer here. And each one of these are just quads that they then rendered whatever that texture got rendered out to be, and then manipulated it with the frame, or the fragment shader. That's the same with the tune and the cell shading things, and like this is cross-hatching over color. So they just took a cross-hatching pixel shader and would slam the color underneath of it. Not too complicated. Like with black and white, it was legit just taking RG and B, adding them to color, and dividing by 3, and then using that as RGB. Any questions with that? Fairly straightforward. Okay, skinning animations. So, there's two different, oh, yep.
I feel like, how many more topics are we gonna talk about today?
3, I think. These last 3 get really quick. 20 more minutes?
Yeah.
All right. Okay, so there's 2 different versions of skinning animation, or of animation. There's rigid, and then there's skinning. You got rigid animation and skinning. So rigid animation is more like a robot, where it doesn't flex, doesn't like give at all. So it's kind of like this guy. If I just rotated, it can only go in the one way, rotating. It doesn't like flex or do a smooth curve like that. But skinning animation does. So each one of these are going to be comprised of a skeleton. So create super simple humanoid skeleton. So legs, arms, head, whatever. With the rigid, it would affect, you could have like a box here. And then anytime this would move, it would move the entire box all at once with this one point. And so each one of these lines are the bones. But when you're talking about skinning animation for the video card and actually programming it, we're concerned about the joints themselves. And a lot of the times they're fairly synonymous. Anytime you refer to a bone, you're actually referring to the joint that it's talking about. And so the difference between the rigid and the skinning is that the skinning affects the individual vertices on this. So if this was comprised of a bunch of triangles here, the skinning animation could apply to each one of these individually. So when this rotated, it would rotate the whole box down, but you could apply different values to each of these. So the box could end up being more curved like that instead. So the way it does that is each one of these joints are comprised of more 4x4 matrices, but in a hierarchy. So usually you'll end up having some kind of like a root joint, or you'll just say, okay, this is my starting point instead, depending on how the artist wants to set it up. I've seen it a bunch of different ways, but just as a way to figure out where the ground is. But then, so if this is the starting point, then you would multiply this one down to this one, and this one would multiply down to this one, so then you could figure out where this box might be drawn at. So if you were to rotate this one, if you rotated it that way, then this whole thing is going to rotate upward. Good so far? Okay. So the trickiest part, the part that I had a difficult time grasping because no tutorial really says that much about it, is the bind pose. So usually when 3D modelers will go in and they'll make a character, they'll do a bind pose, which is usually like it's either an A pose or a T pose. And that just means that's the starting position of the character before they start trying to animate it. And what that does is it says, okay, this specific joint here, here, and here, so this one is rotated like 5 degrees, this one's rotated -5 degrees, and that's the starting point for those joints before we like put a walk cycle on it or anything like that. And the important part for this is figuring out what the bind pose is in the programming part of it, because you want to make it so then this cancels itself out to equal the identity matrix again. So the bind pose is really just whatever its matrix is times its matrix inverse. So the inverse is the bind pose for the skinning. But you need both of them to multiply them together so then it doesn't do like a double rotation on the joints down below it. So when you talk about sending, when you do, you can do CPU skinning, which is multiplying each one of these 4x4 matrices to their individual vertices. Or what's typically done is you send the data to the video card. So you'll send a bunch of matrix 4s, and I think it used to be 62 was the bone limit, the amount of joints that you could have, but it's more or less gone way up. Then you would pass in, so this is a uniform, something that all of these vertices are going to have access to. But then each one of these vertices can have an attribute, an in thing. So if we went back to, if we went back to here, we had an in vector, a position, and a color. We could do the same thing for the skinning animation and do in vector 4 and do weights and in vector 4 indices. Now what these are going to do is for every vertex that we hit, we're going to have these values that we can then do an index lookup into this matrix array. And this matrix array is the skinning, the current state of where the animation is. So if you're in a walk cycle and you stop mid-frame, you could say, okay, let's look at this joint at this point, this vertex, and this vertex is going to need this animation point, that vertex, to multiply out. But each one of these could have, like for an instance, if you had a vector 4, you can have up to 4 joints affect this one vertex. So you could have this joint, and this joint all affect what this vertex ends up being by doing a lookup into here. So this could have like joints 2, 5, and 8. And then the weights, which are you're going to want to equal out to 1, could be like joint 2 is going to do 0.5, joint 5 is going to do 0.3, and this last one will do 0.2. And so you find that matrix, you multiply them all together, and then you multiply it by its A position, which since it comes in as a vector 3, we got matrix 4, and you can decide whether or not you want translation in your animations by changing this A position into that vector 4. So you have A position, and then you can choose whether to do a 0 or a 1. Sometimes you get rid of the translation, like especially with like robotic things, you're not going to want translation because then the arm could like detach or something. And sometimes with even normal skinning animation, you don't want to give that effect, but sometimes you could have like a big fat guy and you'd want the belly to like jiggle or something. That would be translation stuff that you'd want to do instead of doing rotation. But all that determines is if you put a 1 or a 0 in that vector 4, that then gets multiplied out to each one of these matrices with each one of the weights that are in here. Make sense? And so all that does is it gives it that nice curve. It does get a lot more complicated rather with rotations for characters, especially with, like, if you imagine an arm and you're rotating and you keep on rotating, like you get to that 180 degree point and you get back to that gimbal lock issue where you've got the Euler angles affecting it with these matrices. And so you'll get, like the elbow will all of a sudden pinch right together and it'll look like it's just like one point. And you can do dual quaternion skinning, which is, I've never actually done. I've tried looking it up and it kind of boggles my mind. But the idea is that it will give a smoother interpolation like this instead of like doing something like that with this cube, which can look a lot nicer. And then the animation mixing and blending is basically taking this array of matrices and having another set of them but typically on the CPU side of it. So you'd have, this is frame 1 for the walk cycle, and this is frame 3 from the attack animation. And then you just merge the two matrices together to do the blending. And then mixing gets a little more complicated, because if you can imagine a character walking and then you want to attack, but you still want the character to be walking, you either have to like blend the animation of walking with an attack animation that's also walking, or you could like cut it off and say, okay, from the waist down I want the walk cycle, but from the waist up I want the attack cycle. So that would be the animation mixing. And all that that's doing is say, okay, I want for the matrices 0 to 32 of this one and 32 to 60 of these matrices. That's an oversimplification of it, but that's the idea. All good? Okay. Forward versus deferred rendering. Okay, so everything that we've been talking about up until now has been forward rendering, where you send it to video card, it renders it out, and pushes it to a texture. The newest stuff that forward rendering is pretty much always used because of transparency issues, which we'll talk about with deferred rendering. So deferred rendering, which I'll swap to here. Here's an example, actually that I did like a long while back. Is you remember the post-processing effects? You do the same type of thing, but instead of like just changing the pixel values, you put out actual data. So for this one, we put out the color of every single pixel on the screen out to this texture. Then for this one, we put out the normal value for every single fragment position. And then we put out the specular and lighting amount on the third texture. And what that does is, so you've got 3 different textures, and you send each one of those 3 textures out to the video card, and then the video card can then read in each one of those individually to figure out what the end point of these are. And the reasoning for that is for lighting. Because forward rendering, remember when we were talking about that, doing the lighting on a per fragment basis, if you had one light, that is perfectly fine, that's one thing. But you start adding 2, 3, and 4 lights, then you start having to calculate 4 different lights for every single fragment. And as you're going through and you're adding more and more lights, you start hitting a bound where you can't do that much processing, especially per fragment. And so we'll go to, oh, that's fine. So this guy made a really good video that shows it. Although it's a little laggy. So you can see he's got the color up here, he's got the normals down here. He's rendering out the lights as geometry. So right here, he's got a point light that's actually just a giant sphere. So because it all runs through the vertex shader down to the fragment shader, it gets to that point where it can read out each one of those textures to figure out what that specific vertex is, and then calculate the lighting. And because of that, you can get thousands and thousands of lights all to render onto these textures. Does that make any sense? Kind of, sort of? The only downside to this is that when you render out to a G buffer like this, a graphics buffer, which is what the position, colors, and all that, those textures are all called, there's a G buffer, then it's kind of like in Photoshop when you take all the layers and you flatten them. So you lose all of the transparencies and stuff like that you would normally have. So with deferred rendering, you can't do transparency as well without doing like multiple layers of deferred rendering, which is way computationally expensive. Or what most engines do is they will do a deferred rendering pass, and then for transparent objects or super special ones like really shiny, glowy objects or something like that, then they'll do a forward pass over top of it, and they'll superimpose the transparent objects on top of the deferred rendering.
So we need different render layers.
Yes. Yep. Okay, so physically based rendering has been a new term, and so all of the stuff they were talking about before with the diffuse lighting and stuff like that, that's kind of the old initial way to do it, whereas this is kind of a new-ish way to do it, where it's really not that much more complicated, it's just more texture lookups. So before we had the albedo, basically the diffuse amount, whatever color you wanted it to end up being, and then you would so you do the texture lookup and figure out what each one of your values are, and then you would add them together with like certain numbers. You would say, okay, this time I want the object to be 5 times shinier than the last time, so you would take the metalness amount and multiply that by 5. So if you were on a white spot, it would be super, super shiny in that one spot, but in the black spot, it still wouldn't do anything. It wouldn't be shiny at all, which makes it really nice for, like, I don't know, if you're looking at the inside of a car or something like that, you'd have shiny metal spots, trim, and stuff like that, whereas like the glove compartment's probably not going to be shiny. So a texture like that would have a metalness that you could look up pretty easily to decide what's shiny and what's not. That's it. PBR is not super complicated. We have fixed versus variable update loops. Okay, so kind of speed through this one. A variable loop is when you've got your typical frame rate of like 60 frames per second, but that amount can jump and up and down. You could have 37 frames 1 second, you could have 110 the next second. And the amount of time that goes between each one of these frames could vary. Like you could have a super short one or you could have a super long one. And this is what the typical game loop looks like, as a variable time step. So you could have like 16 milliseconds, 16 milliseconds, 16, and then all of a sudden it takes 2 milliseconds, and then it takes 35 milliseconds the next frame. And usually this variable time difference doesn't matter for your games, because usually you're just playing it single player, not a big deal. But when it varies like that, float values can start to sway because of the precision of a float. It only goes out to like 32 positions or something like that. I don't remember. But basically a float can only be so precise. And as you get more and more variation, especially with these variable time steps of how much time it takes between frame to frame, that float can start to vary and drift further and further off. And so what you can do instead of doing a variable time step is do a fixed time step and say, instead of having those, you can say, I only want to do 16 millisecond frames to lock it in at this 60 FPS. So if it takes longer than that to render a frame, not a big deal. We'll skip that whole one and go to an increment, and so it'll be the 32nd frame that gets rendered. The downside to that is that then when you're trying to render these, you get locked into the 60 FPS on your actual video card, or you could get knocked down to 30 FPS if you really wanted to go that low, which most video gamers aren't going to want that, especially if you've got like 144 hertz monitor or something like that, where you can actually take advantage of the increased frame rate. You don't want to get locked down to these. So what you can do instead is, usually the video card will be able to render a lot faster. So in this one time that it takes 16 seconds to render, or to come up with this frame of update for all the physics and movement and stuff like that, you could render 4 different frames in each one of these. So you would have like a 25% one, a 50%, 75, and then you get back to the beginning and you do 0% at the next slide, or at the next frame. And so you do that, and so like 50% of 16 is 8. So you'd be 8 milliseconds into that frame, and so you could interpolate. It's like if you were moving along and you're at 0, 0 again, and you're moving along at a pace of one tick per frame, then you would say at the end of the next frame, the next update loop, I should be at 1,0. But if I want to render at this point, there would be 0.25% of it. So when I actually display to the screen, I'm going to render out at 0.25. And the reason that this can be nice to have is it'll do a locked step. So no matter what computer you're on, because the frame rate is no longer going to be variable, you're not going to start stepping from 2 to 10 to 16 milliseconds per frame. It'll always be 16 regardless of the computer it's on. So your calculations are always going to be the exact same. So if you push down on the A button to run forward for 2 seconds, and player 2 pushes, that's on a completely different computer, pushes it for 2 seconds. The person with a variable loop, they could end up in completely different spots regardless because of that variable time loop. Because it could push it like 0.1, a teeny micro amount over further, versus if you did a fixed, then it's going to update at the exact same intervals, and it's always going to apply the same amount to it. And that comes in handy because of network synchronization and physics. So if you're using a physics SDK, they're always going to do a fixed time step because of that, regardless if your game is a variable looped or not, because you can get away with that too, just by, like if you're 2 milliseconds in and you need 16 milliseconds, it just says, okay, skip. Okay, now I'm at 8, nope, not there yet. 12, okay, not there yet. 17, okay, now I'm there. So then you subtract 16, you got 1 left, now run the physics calculation, and then start this loop back over. Any questions? Okay. Step forward. Data structures. I don't know how much I want to go into. I've got another talk online if you guys are more interested in data-oriented and taking advantage of the CPU and how memory is allocated and shown. And the biggest thing to be aware of would be AOS versus SOA. So you've got array of structs versus a structure of arrays. So it's the idea of, say I've got a vector 3 position and a vector 3 normal, and this right here is going to be my vertex. So this setup is if I had an array of these vertexes, would be an array of structs, where instead I could do vector 3 array of positions and a vector 3 array of normals. And then I could call this my vertices or something like that, some other name. This would be a structure of arrays. So the advantage of that is that all of these positions are going to be laid out in contiguous memory. They're all going to be next to one another. And then all the normals will be next to one another. So if you're doing, especially for like physics, if you're adding positions multiple times to each other or something, adding to those, it makes it a lot faster to loop through that for the CPU. So because of cache locality stuff, which that's a long talk in itself. Versus this, you'll get, if every time you need to look up a certain vertex, you get both the position and the normal. And if you only need to use the position, then the normal is extra data in that you didn't need to deal with. That's sort of the idea of it. But I'll put a link in the meetup thing that has like a full video on it. Just be aware of dictionaries and hash sets and stuff. Not too complicated there, just knowing what your data's doing. Classes versus structs. In C++ specifically, classes when you're doing inheritance, like polymorphism type stuff, and when you create a virtual method inside of a class, it actually creates what's called a vtable inside of the class. And that's added to the size of the class itself. So if you did, I'm trying to think of a good example. Anytime that you add a virtual, it increases the size of it. So if you just had like one float in the table, but then you had a virtual function inside of that, it would add a vtable to the class, increasing the overall size. So instead of the size of a float, it would also be the size of the vtable plus the size of that float. So you can end up with a class that is the size of 8 bytes instead of the 4 bytes that you started with, which can vary based on whatever C++ magically decides. And the only reason that that can be an issue is because of that cache locality thing again. If you have to look up this vtable every time with every single vertex in here, then it decreases the amount that you can have in cache at any one time. And again, the talk goes through that better. Draw calls to the max. So when we're talking about these vertex buffers, you can add all of the meshes into one vertex buffer. So if you had a cube and you had a sphere over here and you had like some prism thing, whatever, you could add all of these into one contiguous vertex buffer and one contiguous index buffer. And then when you render out to the video card, all you gotta do is you bind this once, bind each of them once, and then you say, okay, draw from position 0 and draw 32 triangles. And then start at position 96 and draw 40 triangles. And then draw from there for the prism thing. And the main reason for that is because if you had a vertex buffer for every single object, you're making more and more calls, especially when you start getting into thousands and tens and hundreds of thousands of objects in a game. If you have to rebind a new vertex buffer to the video card every time, then that's going to start getting costly versus just binding it and saying, okay, start drawing from here, start drawing from here, start drawing from here. And that's called mesh packing, just bringing it all together in one big buffer. In which there's a limit to how big those buffers can be, so you have to watch out for that. But that's usually down to the engines. So VAO is a vertex array object. So it's the same concept as this. Instead of having specifying a vector 3 position, a vector 3 normal, you can specify the arrays and say, okay, these are going to go in position 0 on the shader program, and this will go on position 1 for the shader program. And that way each one of these vectors will kind of split out like that. That's all a VAO is, oversimplified. Okay, so graphics APIs. So I've got DirectX 9, 10, and 11 that are the primary ones. DirectX 9 is mostly alive because of XP in China. 10 and 11, they kind of completely revamped the whole thing, and it's a lot better to deal with. So DirectX and OpenGL are similar. They do the same type of stuff, but DirectX is a context-aware system, whereas OpenGL is a globally static thing. So if you want to deal with like a vertex buffer, you bind it, and then that vertex buffer goes up into this global like ID handle thing. The OpenGL says, okay, I've got vertex buffer 5, and that is my current vertex buffer. I can't work on any other vertex buffers except for this one until you bind a new one. Whereas DirectX is context aware, so you can say, okay, I want to update this vertex buffer and this vertex buffer and that one, and you don't have to worry about any of that binding stuff. And then the newer stuff, Metal, Vulkan, and DirectX 12 are all very, very similar. They all come off of AMD's Mantle stuff. Metal only works on OS X and iOS, whereas Vulkan only works on Windows and Linux, and then DirectX 12 only works on Windows. But they're improvements upon DirectX and OpenGL, but they're more complicated to use because they give you a lot lower level access to the video card. So OpenGL, for example, anytime that you would bind a texture or set some parameter saying like make this texture an RGBA, R8 format, something or other, and if it wasn't an allowed format, like the video card didn't support it, then it would throw back an error and it would give you like the text and the error codes and all that. Whereas Vulkan isn't going to give you that. You're in charge of creating, in essence, the driver for your game. But the advantage to doing that is you no longer have to have all of these checks in place to then run your specific game when you're only using one part of their 50 checklist process. And so you can easily get 2-3 times performance based on what your game is doing. Unfortunately, there's still not a lot of video card support for it yet. And then PlayStation, oh yeah, go for it.
Doesn't like DirectX 12 and Vulkan like somehow fix the whole draw call issue where it makes it a lot more efficient?
Yes, yeah, and that's the same thing. It's because of the error checking, where when you're doing the multiple draw calls, because you're with DirectX specifically, when you say to draw a triangle, you just say, hey, DirectX, draw this triangle. But with DirectX 12, instead of telling it to draw a triangle, you're saying, okay, let's build out this command buffer, this graphics card command, and send it directly to the video card. So instead, before it used to be, okay, send to DirectX. DirectX is going to figure all these different commands, wrap it around, do its error checking, and then send it to the video card.
Makes a lot more sense.
And so now that doesn't do it, and most of the time that's good because you don't need 90% of the error checking that it does every time, but it has to do it, especially because of bad programming and things that people do by mistake. It tries to adjust for that without breaking everything. And then PlayStation, Nintendo, Xbox, they all use, like PlayStation uses a form of OpenGL, but it's not OpenGL. Xbox uses DirectX, but it's not DirectX. They're just very, very similar. So cross-platform API stuff can get tricky. And the reason that you need to know any of this stuff is just to have an idea of what it is. It can become handy, like even Unity and Unreal, you can get to the point that you need to start building out your own shaders to do post-processing or special skinning animations and stuff like that. So it can be really handy to start having an idea of what any and all of this stuff does. So it gets pretty low level when you get that far down, but then when you get this high up, you have a much better understanding of what you're actually telling the engine to do. And that's it. This is my engine. Ta-da. So this kind of covers my whole 3-year process of working on my engine and doing this whole multi-graphics API, data-oriented design structured thing. It's on the website. You're welcome to check it out if you want. That's it. Anybody have any crazy questions left?
Are we able to get a slide? Can we get a?
Yeah, I'll put these all up on the meetup page.
Okay.
Yep.
How long will I have my headache?
You need a drink of water.
Yeah.
You've had it for 2.5 hours.
You know, I did grab water and never even bothered. Yep.
Is your engine open source?
So I have it open. It's open closed source. The source is all available. The only thing I have is to pay if you sell your game with it. That's it. Otherwise, educational, personal, hobby, whatever you want to do, make a game with it. But if you put it up on Steam for sale, I ask that you pay for it. That's it.
Is it still under development?
Yeah, very active development by mostly just me. So if you guys are interested, I could use more hands.
How much does motion capture help out with the whole game design?
So that,
When it comes to animation.
right, so that comes down to the art pipeline, which I'm not super familiar with, but all the motion capture stuff is usually going to be put into Maya or Blender or some of those programs that will then help the animator out. But even then, motion capture only goes so far because then you have to start smoothing out the curves and stuff that you get from the motion capture.
Does it do anything to skinning animation?
Yes, yeah. So the motion capture is the skinning animation. It applies, Yeah, so the motion capture, remember seeing like the little white dots
Yeah,
and stuff?
dots, yeah.
Those
Joints.
directly refer to these individual joints.
Okay.
And so it'll apply those rotations.
So does it make it easier to take care of that
It-
section of gaming?
It makes it a lot easier to create realistic looking animations, but even when you get the motion capture in, because of the fidelity of cameras and stuff, there's still some tweaking that you have to do to get the animation looking right. Because you have to like smooth out, like you'll get like the elbows where sometimes it'll look like a little jerk or something, and you just smooth it out. But there's a lot of like some of the universities will release motion capture files that you can then import into those art programs. Yeah.
I think I was gonna choose how you're gonna transition to different animations as well.
Yeah.
Like, so, yeah, basically what you're talking about, like the walking and attacking, you gotta figure out the timing of that.
There's even issues with like transitioning from a walk cycle to a run cycle, because you've got like if you've got the left leg out and you decide to start running, and if the running starts with the right leg instead, and you just try to merge them together immediately, then you're gonna end up having a character that looks like it's like doing a little dance and then running.
Or hitting steps as well,
Yeah.
midway through your whatever run.
Mm-hmm.
I think Dark Souls.
Yeah.
To solve that problem, I said, wouldn't it be more convenient to just use like finite set machines and determine like most common like ways like
Yeah.
left foot, right foot, and then take all of those into account and then incorporate them into that.
Right. So there's another system for, it's called inverse kinematics, which is the idea that instead of rotating the shoulder, rotating the elbow, and then figuring out the wrist to like grab a doorknob, instead you would take the hand, position the hand at the doorknob, and figure out where the elbow and the shoulder were supposed to be. And there's a lot of mathematical issues with that, because like my elbow could be up here. There's no reason that it couldn't be. So there's some issues with that too. But inverse kinematics is usually what you'll end up using in Maya or Blender or something like that. And a lot of times they'll create the like animators. There's like it's like technical animator versus just animator or something like that. They'll create like things on the ground below the character to like manipulate the foot. And so it'll be like the IK handler that'll handle where the knee goes and all that kind of stuff, and try to figure out the blending for it.
That's rigging,
Yeah. Is that rigging animator?
I do a lot of blenders, so.
Okay, yeah. You were the one. Yeah, I want to talk to you
Yeah, no.
about next month. Okay. Anybody else got anything? I think I touched on like half of what I've got.
This is why it takes one game like 3 years.
Yeah. Yeah, if you start doing what I did and building an engine, it takes way too long to make a game.
What was your reason for building your engine?
So initially I was using XNA way back and building a game with that. And at the time, XNA got cut by Microsoft. They didn't officially say no, but they said they were stopping. And so we were trying to decide what to transition to. And at the time, this was like 4-ish years ago, and Unity was just barely even a thing, and Unreal wasn't a thing at the time. So the amount of engines out there available to use wasn't what it is today. Today, if I were to make the choice, I probably would have jumped to Unreal or Unity. But since at the time there wasn't anything there and nothing that I really wanted to use, I started down that path of building a low-level engine, so then we could hit Android and Windows at the same time. And then I just got too far in to stop. Yep.
So some of these things that you showed, how could I guess say if you're using Unity, how could you benefit from that? So I know you said like there's certain ways, but like what
Right.
like an example?
Well, so shaders are one example. You can't really get away from not using shaders, even with an engine doing most of the work. At some point, unless you've got a super simple game, you're probably going to want to touch a shader. But Unity helps because you've got like the asset store, so you can buy shaders and stuff. But even then, if you're making a unique game, a lot of times you're going to have to get in nitty-gritty with that. But then there's more stuff with even like C#. So you'd use the C# scripting for Unity, knowing what like boxing and unboxing for C# is, and memory management of that. And then with the whole AOS versus SOA stuff, figuring those out can dramatically improve the performance of Unity 2. Though they're a little bit different because they use a component entity system, so it can only help so far. Yeah. Yeah. It's hard to say.
Yeah, I don't even know what to ask, honestly.
It's like magic effects. Those always need like crazy shaders that like make it all flashy and stuff.
Mhm.
And stuff like that.
So does the games nowadays, your AAA,
Yep.
are hundreds of millions of dollars.
Or what?
Hundreds of millions of dollars.
Sure,
Call of
right.
Duty, I think was like $500,000, and then
Yeah.
they spent like another half to. So does the money, the expense comes out from the shaders, all basically what you kind of touched on, before you got to like the character models, basically,
Right.
the shaders and the matrices.
I think typically with a game, it's like probably 30 to 40% artwork, I would guess. And I haven't exactly worked for a AAA company, so I can only really
Yeah.
guess. But I would say 30 to 40% is at least that for artwork on like 3D models and all that. And then you've still got the audio stuff and music, and nowadays you've got directors and storyline people and all these things that can add up to it for the AAA games.
What would a director really do? I mean, do they really do anything, or is it just?
It varies on the
I
game.
mean,
Right. Like Jonathan Blow's new game, The Witness, he hired an actual architectural firm to design out the buildings in his game to make sure that they flowed and felt right.
So the director's more the supervisor then, basically, when it comes
Yeah,
down to it.
yeah.
More just
Yep.
making sure the game flows the way it's supposed to.
Right. Yep. Yep. Anything else? All right. Well, I'm going to put the slides and all of this stuff up on YouTube and the Meetup site and all that. I do have the HTC Vive, which I'll set back up if you guys want to wait around to give it a shot. Otherwise, we're all good. All right.